Hello everyone, welcome to the video for Unit 6, Lesson 11, where we're going to do some quadrilateral proofs with segment addition and subtraction. So this is a bit of a review regarding segment addition and subtraction. So remember, there are two different types of things that you can do. They might be giving you something that where you're given, like they say AB is congruent to CD. So right now our given is small. But what we can do is notice that BC is shared by both of these things. So by segment addition, we know that AC is going to be congruent to BD. So to help you understand this, you can apply some numbers, right? So if AB is 3, we know CD is going to be 3. And then BC, we have to give one value to it. No matter what the number is, if I choose 5, then I know AC is going to be 8, and BD would also be 8. So giving numbers sometimes helps you understand. So usually you know you're using addition if your given needs to grow to get what you want. So if we wanted to prove that AC is congruent to BD, right now our given is smaller than that. So if your given needs to grow, you know you have to use addition. And don't forget, when you have shared or overlapping pieces, that's an indicator that you're using reflexive property. Now this is going the other way. For subtraction, your given is going to be larger than what you want. So in this case, we have AC, which is this entire piece here, is congruent to BD, which is this entire piece here, right? And we want to prove, use a different color, we want to prove that AB is congruent to CD. So right now our givens are huge. We need to shrink them. So if you have givens that need to shrink to get what you want, you use subtraction. And again, if you have overlapping pieces, like in this case we have BC overlapping, we need to use reflexive property there. Now these are some general steps that we've used a while back, so I'll have these here for you guys to reference, but I'm not going to read through all of them because we did already visit this, but again, you can use this if you are stuck. And again, just don't forget quadrilateral classification checklist. If they give you that a shape is a rectangle or a square, if they give you that, you're allowed to use any of the properties, right? But if they want you to prove a rectangle, then you know you need to go down the quadrilateral classification checklist in your proof. Also, don't forget, if you're given triangle congruence, you're likely going to use CP/CTC right away. But in this case, I feel like in this lesson, in these types of proofs, you're not going to be given triangle congruence, but you're going to have to somehow prove it using one of these 5. So let's just get right into practice. So again, we're going to map out each of the questions that we do in an effort to make it a little bit easier for us. So let's read this. The diagram below shows square, so I'm boxing that because that is so important for us. And in my map, in my plan, I'm putting square right away because I'm going to write down the properties in a second of the things that we can use. So A, B, C, D, where E and F are points on BC such that BE is congruent to FC, and AF and DE are drawn. And we want to prove, I'm going to put we want to prove in blue, we want to prove that AF is congruent to DE. All right. Now, what's standing out to me, I have the shape, they gave us a shape, so I'm going to write down the properties that we might use from this shape. So in a square, we know all sides are congruent, we know all angles are 90, and we know a couple of other things about diagonals and such, but in this image we don't have any diagonals, so I'm not even going to write those down. All right, now that that's out of the way, let's try to come up with a game plan. So we want to prove that AF is congruent to ED, so the first thing that you should test is, are these sides corresponding pieces of different triangles? So let's highlight the triangle that AE is a part of. That's triangle ABF. And let's highlight the triangle that DE is a part of, which is DCE. And it looks exactly like that. They are literally the same exact, they're in the same location. AE and DE are in the same location of both triangles. So what that tells me, when I have sides that are in the same location, I'm going to use CP/CTC. But before we use CP/CTC, before this, we need triangle congruence, which the question does not give us. So before this, we need that triangle ABF is congruent to triangle DCE. We need that before we can use CP/CTC. And to prove the triangle congruence, I'm just going to start writing the proof out because I feel like that's thinking a little bit too much ahead here. So let's use our map to get started, and then maybe we'll see where we can go. So statement, we have ABCD is a square, and we have that BE is congruent to EC. And that's given. Now, the second thing I'm doing right now is I am addressing the properties of a square right now. So I know BC is congruent to AB, is congruent to AD, is congruent to CD. And that's because in a square, we know that all four sides are congruent. And I'm going to combine this. In this same statement, I'm going to say that angle B, which is right here, and that angle C are right angles. And you can separate this. You can put a third one, but I'm going to add to my reasoning. In a square, all four sides are congruent, and all angles are 90 degrees. You could separate this if you'd like. Now, you might be asking, why didn't we say that angle A and angle D were 90 degrees? Well, you can, but it doesn't really help you. Remember, we're trying to prove that our blue triangle and our green triangle are congruent to one another. So if we're saying that angle A and angle D are right angles, these two angles right here are not a part of either triangle. Like, part of the angle is inside of the triangles, but the entire angle is not. So that's not really going to help us, so I'm leaving it out. Okay, so far, where we're at, in both triangles, I have a side, an angle, and that's it. So my goal, I'm going to try to use SAS. So I'm going to try, I'll add this to my map, try to use. But in order to use SAS, I either need, well, I literally only need this side right here. I need this side for the blue triangle, and then I need this side right here for the green triangle. So in order to get that, what's standing out to me is that I have givens that are a portion of that side, and then I have this EF overlapping here. So you know what? I'm gonna get that out of the way right now. So EF is congruent to EF, and that is by reflexive property. Now, in the past, when we're using segment addition, we were making a bunch of equations and using substitution, but you don't even have to do all of that. So I'm going to teach you guys a life hack to make your proofs a little shorter that the Regents still accepts. So right away, you can just say that BF is congruent to EC, and the reason there is just segment addition. Because in the Regents, it's understood that if you have this smaller part to be congruent, if you're adding the same value to those pieces, the result is going to be congruent as well. So there's no need to make all the equations. This is perfectly fine. Now that we have BF being congruent to EC, now we are able to use side angle side. And remember, side angle side is your reason, and you use that to justify the congruence of triangles. So ABF is congruent to DCE, triangle DCE, because of side angle side. Now, once we have triangle congruence, now we can use CPCTC here. Now, remember, these segments AF right here, and ED, those were corresponding pieces of those triangles. So I know now AF is congruent to DE because of CPCTC. And that's all. And don't get fooled. A lot of people, when they see right angles, they're like, oh, we're going to use HL, we're going to use HL. That's not always the case. So just be very, very mindful of that. All right, now we're going to go to the next question. So the next question says, the diagram below shows rectangle, super important, ABCD with points E and F on side AB, segments C, E, and DF intersect at G, and angle ADG, which is right here, is congruent to angle BCG, which is right here. And we want to prove, let's write this in blue, that AE is congruent to BF. So let's write our map out. So in our map, I know we have a rectangle. So let's figure out the properties that we think we're going to be using here. So in a rectangle, I don't have diagonals here, like DF and CE are not diagonal, so we're not going to use those properties, but I do know that opposite sides are congruent. And the other property was that all angles are 90. So that might help us out here. Now, I'm going to start writing my proof out, because sometimes with these, it gets a little bit complex to map out the whole thing, but if you can, please do it. So ABCD is a rectangle, and angle ADG is congruent to angle BCG. That's our given. And then right away, I'm gonna, or you know what? Let's actually evaluate this. So AE and BF, to me, again, those are not alone. They are not sides of any triangles alone. So let's see which sides they are, or which sides they are a part of. So AE seems to me that it is a part of this triangle in blue right here. Now BF is a part of this triangle in green right here. So again, a lot of these proofs involve proving the congruence of two triangles first. So it's important to first figure out which triangles do you even need to prove congruence of. So I know I need to prove triangle ADF to be congruent to triangle BCE. I know that has to come. And then I know I'm going to use CPCTC after that. And then we'll work on, I know this is going to be addition or subtraction. Again, I know it's addition or subtraction because the given that AE, or what we're trying to prove, AE and BF, those are not parts of sides of triangles. So we need to either use addition or subtraction after we use CPCTC, but we'll address that a little bit later. So my second statement is going to address the properties of our rectangle. And again, these properties should help us prove the congruence of the two triangles that we want, right? So opposite sides are congruent, yes. However, the only thing that's really going to help us is saying that AD is congruent to BC, right? Having AB and CD congruent doesn't really help us because they're not parts of the triangles that we want. So I'm only going to state that AD is congruent to BC. And then again, same thing like we did before with the angles. All four angles are 90 degrees. However, not all four of those angles are within the triangles that we want. So I'm only going to say angle A and angle B are right angles. And the reason we have to be specific here, so in a rectangle, opposite sides are congruent and all angles are 90 degrees. Now remember, when you state 90-degree angles, you need to go the extra step and just say, hey, angle A congruent to angle B because all right angles are congruent. Great. Okay, so we've done the rectangle stuff. Now let's see if we have enough to prove the triangle's congruent. Now again, don't get tripped up. If you see a right angle, don't automatically assume we're doing HL because we're doing something else actually. If you look in both triangles, we have an angle, a side, and an angle, and in this one, angle, side, angle. So that is the theorem we're going to be using. And again, remember these theorems are reasons and they are justifying the congruence of triangles. So triangle ADF is congruent to triangle BCE. And then right after that, we need to use CPCTC. We know that is coming right after. We just need to figure out which parts are going to be beneficial to us here. So again, we're trying to prove AE is congruent to BF. So it only really makes sense to make a statement about the sides that those are a portion of. So AE is a portion of AF. So I know I need something about AF. And then BF is a portion of EB. So I know I need something about EB. So AF congruent to EB by CPCTC. And now I need to figure out whether I need to use addition or subtraction. So right now we know that this larger piece and this larger piece, those are congruent. That statement, what we've concluded, needs to shrink to get AE and BF. So I know I am using subtraction, but again, I just want to make sure we are addressing the overlapping piece of EF. So EF congruent to EF by reflexive property. And then last but not least, again, we don't need to make all the equations. It is an understood phenomena that if you have two larger congruent pieces and you're subtracting the same thing from them, the results are going to be congruent. So we're good. AE is congruent to BF because of segment subtraction. And again, if you wanted to make your equations, you can. That would just make your proof a little bit longer. And that's it. So sometimes with these, might be a little bit harder to map out the entire proof because you're looking so far ahead, like figuring out whether you're using addition or subtraction. So at least map out the first couple steps. At least figure out, if they give you a shape, figure out the properties of that shape that you're going to use. Figure out the triangles that you need to prove the congruence of, and then you can go ahead and get started.